So I'd like to introduce our next speaker is Keith Brady from Renishaw. So Keith is regular guy here, yeah, at CCAT and Renishaw and their equipment. So Keith is going to be talking about powder bed fusion. When we think of powder bed fusion here at CCAT, we look at the technology that's probably the prevalent manufacturing technology in use today. It's the technology that is probably the most mature from a research and development, from a sensor and quality control perspective. And so there's a lot of reasons why it's probably the leading metal technology. So with that, Keith.
Thank you very much for the introduction, Jeff. Thank you for the CCAT team for the invitation to speak today. We certainly appreciate it. I feel very at home, certainly surrounded by Renishaw equipment. So the relationship with CCAT for Renishaw has been long-standing, certainly very valuable for us. I think on the additive side of things, we look at the perspective that CCAT brings to this conversation is extremely credible, right? It's a additive center of excellence, you know, whether it's on the laser powder bed fusion side, hybrid type processes that they have on the floor here, what we do with sort of conventional laser powder bed fusion, as people have come to understand over the years. But then additionally, you know, what's done with, you know, Mark Forge's efforts in this industry, what people are doing with plastics. I've been in additive for a whole 4 years effectively, and I come out of the water jet industry previously. I'd like to believe that we brought the water jet industry from black magic to commodity being not nearly as entertaining, frankly. So coming to additive was to try to get back to some form of black magic. And I think there's enough black magic in this industry to go around. So I think that to have a room full of users, right? This is a nice small event. So I think just a great effort on CCAT's behalf, not only to have users here, but to have industry experts coming together to have candid conversations that revolve around applications. As an additive team here at Renishaw, we've certainly arrived at the notion that real applications, real parts, real things that are brought into production has now become the focus. If we print trinkets, if we print bottle openers, those are all cool things for people to carry around. But people want to talk about how it is that the technology could impact their business, generate revenue, what skill sets do you need to deploy it, and how is it that you sift through all the options to get where we're going. CCAT has been instrumental in, you know, just me understanding that perspective better over 4 years. And then I think, you know, I certainly appreciate what Andrew's conversation this morning, Francesco, Gabe, your conversation about the breadth of technology that you have and where it fits, right? For us, a majority of the conversations we have with prospective customers is how does it fit? So just curious, with potential additive users, show of hands, who has actually deployed the technology, additive in some capacity? Right, so 4 or 5 hands. So with a room full of 25, 30 people, right, we've got industry people, and then we've got those that are adopting the technology and pushing it forward. So we thank you for that, certainly. But I think for us, our mandate is to ultimately figure out how it is we help people generate some revenue, get some problems solved, and get this industry moving ahead more quickly, right? So as you see, as I refer back to the Renishaw equipment, we are a company that has in its roots process control. So this is an Agility CMM. It's equipped with a Revo 5-axis probe on the end effector. It has a tool changer. There's an equator in the back of the room, which is effectively a digital gauge. Thank you for the assist over there, by the way. But we are a company that is rooted in process control, and we often get questions like, I didn't realize that Renishaw was in additive. An interesting twist recently is that people will say to us they didn't realize that Renishaw was in metrology, which makes us actually happy on the additive side. So, but it is the company's involvement with additive, outsourcing it, that brought Renishaw into the fray to try to understand what the technology could bring to bear. But more importantly, as we purchased a company that manufactured these systems and to go in a different direction as an organization, it was for us to understand the technology, determine where our core skill sets could contribute to this effort, and then quite methodically just start driving it forward. And we have our spot, 10 by 10 inch build volumes, 13 inches in Z. We don't make big parts. We don't talk to SpaceX aside from being interested in what they do, right? And we think that companies like Aerojet Rocketdyne, you know, what they're doing with large parts is phenomenal work, right? But for us, it's going to be a matter of continuing to focus on what we do well. And that brings us into this, this area. That's the easiest way to talk about this. There we go. It brings us into the area of how do we use our core expertise to set this forward? Little historical perspective in the back of this picture, upper left, that is Renishaw's initial facility in Gloucestershire, England, about an hour and a half southwest of London. And you can see in the lower right, just about the middle of that photo is Renishaw's facility now. So that's growth over the last 40 years. With that growth has come growth here in North America. This is Renishaw's North American headquarters located just outside of Chicago. This is our North American headquarters, means that the metrology team finds a home here. The additive team certainly finds a home here. And when we talk about metrology and machine measurement in general and process control, we're involved with virtually every industry. We like to say that most parts that were ever produced have somehow been touched by a Renishaw tool at some point in time. So again, some things we have here included in this picture, but things like laser interferometers, ball bars, styli, all things that if you know Renishaw any other way, that's what we're coming to know. Surgical robot systems. For Parkinson's patients, surgical robot systems allow a surgeon to have a mechanical assist effectively with a high precision robot that can position an end effector in a sleeve so a surgeon can precisely make an entry into a patient's skull and place either a direct medication or an electrical impulse probe or something similar. And it's done a tremendous amount of work, to help patients that really needed these kind of therapies and these advances. You'll see an inset there with some software that was generated for these tools by Renishaw, and it turns out to be a core piece of software that we use on the additive side. So I'll talk about being vertically integrated. Raman spectrography, the best correlation I can create for this equipment is that if you had a pill and you wanted to know the distribution of its elements, this can come into counterfeit drugs. It can come in with dangers that come with counterfeit drugs. You can actually look at a pill and determine the distribution of components in that pill and determine if it's counterfeit. So pretty cool stuff. I'm sure if I had a ramen guy, they would be cringing with that shallow touch on that. In terms of products, Renishaw manufactures encoders. That's not something that most have any sense for. We manufacture enough encoders that we can effectively refer to it as a canary in the coal mine with manufacturing. We can tell what manufacturing is doing globally by the amount of encoder sales that we have, okay? So, and this allows us, all of these different disciplines and, our different vertical integration points. Upper left there is our manufacturing facility in England. And Renishaw is first and foremost a manufacturer. Most things that we have developed has been to put us further forward as a manufacturer. The first product Renishaw ever developed was a 3-point touch trigger probe. And that was basically to identify a point in space to quantify something. And our current chairman, still here in his 80s, developed that product. And then the challenge of manufacturing it led to everything else that we've effectively done. So great organic story, right? But, and we know in the end here, in the lower right, we know that we can print parts. We know we can print parts and try to quantify them. We can do all kinds of things, but trying to measure these parts can become tricky. And frankly, we don't have the answers. We have the tools, we don't have the answers. So we have to engage with industry, not only to print parts properly, quantify how well we've done that, do it repetitively, do it repeatably, reliably, a whole number of different things before this technology that we've invested in comes of age, right? So that, I need to get better with my slide advance here. This is it's pretty rudimentary, right? But laser powder bed fusion basically is a micro welding process we use as a point of reference, an 80 micron spot. That allows us to print delicate features. I'll hand this over. How thin a wall we can print, how delicate a feature we can print. Laser powder bed fusion is good at creating intricate detail, allowing us to create these parts that have effectively wrought properties. A lot of it, you know, I've heard it time and time again here this morning. Application, depends on your application, depends on your application. We know that everything comes from the application out. So that's a demonstration of thin walls. If you look at this, you know, this basic set of parameters, I don't want to turn away from the mic here. But if you look at this basic set of parameters, we've got a beam that's a certain width. We lay down a certain thickness of powder. A lot of applications work with this, right? Particular type of powder, certain particle distribution within that powder, and we effectively weld parts layer by layer, penetrating the previous, and that gives us this wrought characteristic for the material. It suits certain applications. I look at so many things with like binder jet, and think that binder jet printing makes more sense, certainly, than anything we can do in terms of speed. Increase the criticality, take certain features and change that story a little bit, right? And then laser powder bed fusion can find its home. This parameter set, right? I'm sure everybody has gone to any multitude of presentations or events and learned about these technologies and learned about them to the nth degree. I have spent certainly a good portion of the last 4 years wondering if I've been in the right room, consuming a presentation about defects and stochastic defects and spatter and smoke and everything else we come up with, right? But at the end of the day, we've got to figure out as a group, I would say as an industry, you got to figure out how it is that we take this process, quantify it, and then get down to, can you print it? How long does it take? And how much is it going to cost me? So this, this process, I think what Renishaw has brought to the industry, certainly this is a quad laser system. So in Renishaw's evolution with additive manufacturing, right? There's an AM400 on the floor here. It had a predecessor, an AM250. Those were a company called MTT designed those machines. Renishaw bought MTT, and we learned a lot once they started wearing a Renishaw badge. These systems that you see printing here, this is a quad laser, what we call a 500Q. And this is truly a 4 laser system. Again, the same 10 by 10 inch by 13 inch build volume, but we can print parts more quickly with 4 lasers. Right, and you can watch that process. I don't think, unless anybody wants to disagree with me, I don't think anybody would describe this as a fast process at all, right? Not uncommon that we're printing 25 plus hours, 48 hours, 60 hours, right? So this is what these machines look like. This is a material flexible machine. I use this picture to lead it because this is the next generation of the AM400. Effectively, it's sitting on your floor. And what we ask, and when we start talking about applications, we go through these items that I've listed here. Do you need single laser? Do you need multiple laser machine? That's usually a production type question. Is it a single or a multi-material application? Then we know whether or not the machine could be single material or whether it has to be multi. Multi creates certain challenges. Is the industry regulated or non-regulated? You know, if you talk to the aerospace guys, printing two different materials, if it was aluminum and Inconel in the same machine, that's not gonna work. And then, you know, if you take the bar a little lower, when we talk to the Department of Defense, they don't have that criticality. We can sort of take, you know, back off a little bit, and then the material flexibility piece is allowed, or is it more practical? Or if you're doing material development, then yeah, you know, maybe this is a great machine to start with and have as a foundation or an ongoing reference, right? So that's a picture, just a picture of a multi-material system. This is a production system. By a production system, I mean a machine that has onboard powder sieving, less interaction with, you know, from the operator with powder. It keeps the material stable, so in an argon inerted environment more often. What it effectively does is it gives us production capability and process control that allows us to be reliable, repeatable, and then on point when it comes to mechanical properties and all that type of thing. This is a depiction. If you look at why multi-material machines can have a benefit, let's keep doing this. So on the right-hand side there, you can see that that's what we call a total loss machine. You introduce the powder, it goes down into the build chamber, it overflows into flasks or, you know, containers down in the lower section of the machine, and you sieve that powder again to reuse it. You determine how many cycles are acceptable, that type of thing. But easy to clean out. When you start looking at these powder paths, much simpler on the right than it is on this system on the left, which is designed to be single powder use, where we recirculate the powder with the gas circuit. So that's not a machine. We can clean it out, but it's not a machine that you really want to be cleaning out very frequently. All right. So for us, number of lasers, multi-material use, and can it be a single powder machine? And then we can close it up and do onboard powder recirculation and that type of thing. Materials. This is a very short list of things that I would tell you that we have developed parameters for. I'm going to say that in a pretty qualified fashion. Insofar as we think a developed parameter set is that you've done thin wall, bulk, you've developed a parameter set that allows users to succeed generally. We know that this usually refines so that you end up getting more on point with your geometry as time goes on. We have these materials. Renishaw's approach to this is to make these available to all of our customers. So anybody who wants to use one of these materials, we provide the parameters as part of being a Renishaw customer. Some of the ones that are a little unusual, that is CP copper in the center there on the top, and that was printed. That's coming off the machine like that, and that's with a standard system. There's nothing unique about the laser or anything else, right? So we would like to believe certainly that that has a lot to do with process control. We sort of drink our own Kool-Aid, if that's a good way to refer to it. This is the heart of our machine. It's the galvo block. We print it from aluminum. We print it on one of our quad laser systems. Ultimately, if we don't get this right, these machines aren't going to be what they need to be. So if you take a look at that assembly middle center, we're actually doing something with a hybrid print process. So we use the build plate as part of the final assembly. So we're also trying to take this from a manufacturing perspective. We're trying to make this as practical as we possibly can. Because if it doesn't make sense to us, we're not sure that we could certainly have it make sense to others. You can see the fully populated version of that, right? If it's a quad laser machine, there's going to be 8 galvo mirrors in there. The idea behind this, as depicted in that lower center picture, is that all the lasers can access the full build plate, and they can all do exactly what we need them to do during the build process. So there isn't multiple assemblies that sort of add to the complexity of what we have to consider. So that's a production application for us, right? The galvo blocks are part of every machine we build. They're part of our production process. In my estimation, the medical industry is about the most mature industry that I see personally. If you ask the guys on the medical side of things very often what they do and how they look at defects and all the complexities of the process, they'll say that they print parts, they do it in production, they have the data, they have a level of confidence, and that they don't have nearly as many overarching questions or concerns as other industries do. So they're in a good spot, right? They're making money, they're producing thousands and thousands of parts, and they make sense, frankly, for all of us, right? So cranio-maxillofacial components, I don't have one of those parts, but I'm handing the part that I just handed around here is part of a knee. So when you look at these cranio-maxillofacial implants, they're all personalized, as you would expect, right? It's not a one-size-fits-all or a product line. We're all different. So if you have a facial injury or a cranial injury of some sort, the people that are in this industry are ultimately in a spot not only to produce personalized parts, which is bespoke. They don't have the advantage of standard parts that they can keep putting on their shelf. They normally have short turn times, 3, 5, 7 days to ultimately get a patient the care that they need with the components that they have to get to them. So their turn time is quick. This part that I'll hand around is actually a cranial plate. So if you had some kind of they'd go through and CT scan the injury. They provide that digital file effectively. The hospital or the practitioner would, provide that to whoever the manufacturer is, and they're going to print that part. They got to go through a QA process, and typically, as you can see in this picture here, they match it with a plastic print. That becomes part of a surgical planning process, and it allows them to have an early on QC check, see whether the part fits. So I don't know about anybody here, but you start thinking about where this stuff really, where the rubber meets the road. This is yeoman's work when it comes to what this technology is capable of, right? And it's not easy. I mean, the personalized piece of it makes it tricky, This industry is starting to move towards qualifying the process too, right? Not necessarily a particular machine with a particular powder, done a certain way where they've got a recipe. They want to qualify the process itself. What are all the applicable parameters? They want to produce on these machines that have options on what they do and be able to more seamlessly move ahead as time goes on, right? So again, I think they're the most mature. This is a Renishaw case study, so you'd be able to dig it up. I don't want to show the case study as it sort of is printed, but this to me is practical. You see the surgical plan on that upper left. You can clearly see the individual and the injury that he has and what impact that would have had on his life. And to me, that's life-changing, right? Local company, parts in production, right? So parts in production, generating revenue, more answers than questions, I would say, certainly for these folks. So Mott is a company in Farmington. We had certainly the pleasure of having them join us at AMUG. I think that the work for anybody that, show of hands, anybody know who Mott is? That's pretty good, yeah. So what Mott does is they print parts with engineered porosity. They would make an argument that if you understood this process, engineered porosity requires your process to be more on point than fully dense. So they're taking gradient porosity, they're putting them adjacent to each other. In this case, this is a mixer. And they're actually, those tubes have got different porosity individually. And then they have a center tube that they can either draw or push through, right? And then on the top and the bottom of this part, they're fully dense. So all their interface parts, so they're doing it all effectively. They're doing part consolidation, they're doing fully dense, they're doing porous parts, and they're doing this stuff in what they would certainly describe as short run production. They don't make 10,000 parts a year. They make maybe 1,000. Yeah. So this is Vince Palumbo is the guy we work with at Mott. Again, anybody that I would certainly encourage you to look Vince up if you'd like. I connect you with him, but Vince is a great guy, pretty humble, and understands this business. And this is an idea for anybody that. So I'm the sales guy, so I'm not the technical guy that's going to start going after all these particular points of design, but you know, they get hit all the time with how well they can control porosity and what sort of the max and mins and allowables are, but a lot to it, right? If we're going to try to validate a machine design, for us, it's the point. You print parts and basically you validate the fact that they're consistent, that they're mechanically stable, or mechanically repeatable. And if we were going to employ these machines in our manufacturing environment, like we do, and we start to expand that, we got to know that they're consistent. Right? So for us, there is no other way to validate consistency, and everybody sees these slides. But to us, you know, if we're running stress strains and they have a parallel to rot, obviously that's where we want to be. We need them to be consistent. We need them to all be predictable. And this is stuff that we do with regularity. So this is why Keith's wearing glasses. So right, that's tie 6-4, and this one's Inconel. Right. So for us, it's just a matter of making sure that these patterns or these curves are matching. So we're very happy with the way the machines perform. We think that that serves the industry well, and for people that want to do things and just print parts and not continuously worry about whether they're consistent, this helps, right? These are all, if you look at that map, the quad laser machine, you can tell by the color which laser was printing. We print with all the lasers adjacent typically, and then they all build into the wind for obvious reasons, right? Or into the gas flow. If we wanted to take this concept, each tensile specimen, getting pulled, getting printed, getting pulled, tested, we look for consistency, this is a responsible thing for us to do. Renishaw is highly data driven, so it's the only thing that makes us comfortable, frankly, is to keep doing this. The next level is to take that and print each tensile specimen with 4 lasers. That'll tell you how well aligned your lasers are. It'll tell you how consistent they are. It'll tell you how they behave in proximity to each other. And again, if you can get those results to interleave on each other, then we feel pretty good that we're doing well, right? Process monitoring. So I pause here just in terms of how we get these questions, I think, you know, from the sales perspective and certainly our applications people. If we have data and we have parts and everything looks good, what data can we collect? What further assurance can we provide that every time we make metal, which is effectively what we're doing, right? So we're going to make metal every time, which turns most conventional manufacturing on its head. If we're going to make metal, how do we know that we're making metal consistently every time outside of tensile specimens? How do we make it so that this process can manage itself in some ways, or otherwise let you know that something's gone off track? So that we have a build chamber camera, probably the easiest thing we do. We take a picture before we recoat, we take a picture after we recoat, and we're just looking for results. Down below, we actually take a look at the emissive characteristics of a melt pool. I say emissive because it all works from a particular reference point. It's not thermal. I mean, it's bedded in thermal. But emissive basically means that we can get a voxel by voxel representation of what that build looked like. And I would tell you for the future, we're starting to use APIs so that industry partners on the software side will develop tools, AI, however you want to describe them, that'll parse through this data. And I think, you know, one of the things I hear in the aerospace sector is that, you know, you hear it from the standards guys. They're trying to develop standards. Everybody's asking them why it's taken so long. They're asking them how they're going to get there. And the standards guys want to certainly say that there's not a consensus yet as to how this should all come off, right? So for us, we're waiting for the same thing. We can collect data, but we have to have a consensus about what's good, what's bad, what are we going to act on? Are we going to act upon it, or are we just going to advise? This is very similar to what we do on the metrology side. These two pieces of equipment, CMM, typically we use a CMM, we actually measure a golden part. We take that particular profile, so that's the gospel part, right? That's what we're gonna go by. We take that, load it into an equator. The equator is the digital gauge. Now it's gonna compare that part in a very simplistic form to the golden part. And we're gonna say, yeah, we're good. We can give you deviation and everything else associated with it, right? We anticipate we should be able to do this eventually. This will be our golden part. And then we'll be able to look at it and say, if it's with a certain level of confidence, we're good to go. The thermally or, this history gives us some path home. This is just an idea. If you had further sort of thoughts on what we're doing, we can measure laser power while the machine's running. There's a whole bunch of 2D data that we collect, as Jeff had mentioned, strength of the technology. And then for a quad laser machine, a terabyte per hour of data. That's a trick. I can tell you it's a trick every time that, we have a customer that wants to take a look at the software and you have to give them a data package to somehow use. What are you going to do with that? Say, okay, sure. You get a spot where I can download half a terabyte of data. So how this is going to be managed, how this goes forward, I think we could all have a quick conversation and say this can get out of hand pretty quick. Do you collect it all and then compare it and it's good to go and then the data just gets dumped and then you keep going? You're going to make it a historical thing? Because I think that'll be a problem. So this is just an idea of what we're doing. So it's a missive, right? So we have a separate functionality in the machine. It's not on a standard machine, but an ability to not only print parts, but collect relevant data and put it away for reference. I'll buzz through that one. I've heard certainly, one of the mandates here at CCAT, our equipment reflects that. Certainly, by the way, the facility looks great. You guys have shaped the place up beautifully here, right? So the Industry 4.0 conversation, whether it's Industry 4.0, digital manufacturing, however you want to characterize a lot of these things, again, we don't have all the answers. So we have tools that can ultimately play into that, and we know that that doesn't exclude additive. So if you hit a home run, you're going to start printing parts. You realize you can print them at a certain rate, but now you're going to need 20 machines. How is it that you collect the data, manage them all on the floor, and otherwise make sense of that, and then more importantly, integrate it with the rest of your shop, which is what we have to do. So this is just a reflection. We are well positioned to do that and have a lot of tools to speak to that conversation. And this is really just more of the same. And with that, that is the end of my presentation. Any questions? Right. Okay. Haywire or whatever. Yeah. So the question was, with long print times, can we reliably, effectively leave a machine and have confidence that the parts will complete? So the answer is yes. So I'll use the craniomaxillofacial. As anybody, we all can learn that from this discussion, right? But the CMF guys, they receive cases every day. They basically aggregate those cases all during the business day, and then shortly before they go home, they hit run on the printer, and those are relatively low height builds, but they're going to take them 12 hours, 11 hours. So they hit go before they leave, and then they come in, and those time critical components are produced. So the confidence level is high. That doesn't suggest that there's not the occasional problem. That's our job. Our job is to make these systems robust, reliable, and repeatable. And if you put multiple machines in a spot, be good at it. Otherwise, the industry will lose confidence. Yeah, I think it's how you want to look at it, right? If you had some kind of real critical issue like a part, pops up on the bed or something, and you have your recoder, which is a mechanical mechanism, physically hit it, yeah, the machine will stop. There's certain things in terms of sensor data that if we see things like oxygen level, process parameters go out of bounds, we can stop the process, right? And we do that in sort of different capacities and to different extents over time. Yeah. Answer your question? Excellent. Any other questions? That either means I did well or everybody's getting burnt out here. So. Yep. Yeah, I think that my personal perspective is that the level of adoption is certainly increasing, and I think adoption is an important word. Interest is one way to look at it. Adoption is something altogether different. So when we go to shows now, you know, various events, you have far more companies that are coming talking about how it is that additive is going to be part of their capabilities and how they're going to move forward, and they have something that they want us to look at specifically. Increasingly, I think, you know, with a number of different colleagues here, you know, you have to have a process that's thorough. So to me, that's extremely encouraging, right? So if the adoption rate is increasing, the requirements are certainly scaling as well. I think that'll bode well for the future of the industry. How quickly, who knows? I mean, if it's, what somebody say earlier, 25% or so over the next 8-10 years. So, yeah, we'll see. I think there's a lot of work to do. Okay. Yeah, all right, so the question is, can you take an existing part effectively and print on top of that part, right? So have a multi-stage process. Mm-hmm. Yeah, so the answer to your question is yes, it is possible. We have a customer that joined us at AMUG time before last that actually brought some great concepts to this. They make molds, and oftentimes they either have to, restore that mold or otherwise, improve a feature on it or add something, or they add vents, which is another porosity type application. You have to apply a certain level of care to it, but it absolutely can be done, and I think you can do it with a level of confidence that you've done it well. So yeah, not something that we advertise typically. I think industry-wide, right, when you look at the next conversation here is DED, I think that when you're talking about adding materials to existing parts and stuff, other companies that we obviously see in conversations around the industry are doing a lot in that regard. So perhaps maybe more to come. It's a question that what's the average pore size? So I'd have to effectively check with our applications guys to see if we've come up with something that's sort of an average. We look for defects more than we do to define porosity. Is the real it's the real answer. So. Oh, in terms of, for instance, so are the pores interconnected or isolated? I'm going to use Mott is the authority here. They can be interconnected, and Mott refers to that as tortuous path. So the answer is yes, they can be interconnected. Mott also has applications where they have porosity that is characterized in different areas of the part to perform different ways. So, all set? Very good. All right, folks.